Up to now, we've looked at CCDs and near-infrared detectors, but focusing on taking images, but the process of using them to take spectra is relatively similar. The main difference is, instead of just having your telescope, a filter, and then your CCD, typically, instead of a filter or in addition to a filter, you have a prism or a grism that will disperse the light. Essentially, you have a spectrograph. That spectrograph will split the light into wavelengths or frequencies, and only then will the light be projected into a CCD, so that per pixel, you'll no longer be getting a flux, but you'll be getting a flux density, because the flux has actually been dispersed by a spectrograph. An important thing to realize is that even though you might be familiar with spectra that looks like this, you'll be able to see in the x-axis wavelength and in the y-axis flux density. The reality is that the raw data will look very, very different. This is data after it's been fully processed and actually extracted. Real spectroscopy data on a CCD will actually look much more like this. You also have this example in the lecture notes with the full description of what you're seeing, but I'll try to guide you through some of the main features. In practice, what we're seeing here are actually different spectra. There's one here, another one here, another one here, here, and also even back here. This instrument is actually able to take many spectra at the same time. What you also notice, and we can focus, for example, on this object, is the spectra is just this part. Wavelength actually runs from here. This is shorter wavelength, longer wavelength, and this is the spectrum. The way that you would see the 1D is essentially by collapsing all these pixels together for a specific wavelength and then extracting along this direction. You'll be able to see some continuum, and here there's a faint emission line that you can see. The other thing you may notice is that all these slits, so these are called slits, have these bars running along. Some of them are faint, like this. Other ones are really bright. And these are still spectra, but they're not coming from your astronomical object, which is here. They're coming everywhere within the slit. And that is because their lines originate in our own atmosphere. They are actually skylines from OH molecules. And for spectra, this is one of the things that needs to be removed. This is raw data that we can see here. On top of that, you may be able to recognize in this spectrum a very bright emission line, for example. But also, you may be able to see these things, this one, or even this one. These are cosmic rays that the CCDs capture. So this data was actually taken as part of a very famous observing run where we discovered and measured the distance to the CR7 galaxy, and specifically the data where CR7 was. You can actually see it in the raw frame. This is an emission line that's Lyman alpha transition from n equals 2 to n equals 1 that happened almost 13 billion years ago. In this case, wavelet is actually running in this direction from down to up. And then once you extract the spectrum, this is how it looks like. Typically, spectra will be calibrated in terms of wavelength, and in this case, it means calibrating the Y pixels in terms of what they mean in wavelength, and also calibrating these counts in terms of flux density so that we can actually plot it here. Something to be aware is that some instruments will have slits, and you actually use lasers to cave the slit so that once you put your mask in front of your telescope, then your slit will be exactly at the place where you want the object to be before it gets dispersed by a spectrograph. In other cases, like the example that you see here, you actually use fibers, and typically you have a tiny little robot that will place the fiber for you, or you have to do it yourself. Typically what you do is you already know which stars or galaxies you want to study. You need to convert essentially the X and Y positions of your plate where the fibers will be placed into right ascension and declination, and then you try to optimize the problem so you can try to put all these fibers. And this is a real example from some of my observations. And one of the big difficulties is that fibers cannot overlap. Therefore, there's a limit into how many sources you can actually observe before fibers start to actually collide. Once you actually place them, and if you do it well, so that fibers are seeing the star or the galaxy that you're looking at, each one of these fibers will conduct the light to a spectrograph, which will disperse it, and then finally you'll be able to get data like this. There will be no spatial information because fibers will just capture the light, and then essentially that information, that spatial information, is lost. But you'll still see something very similar. Each one of these lines is a spectrum from a real object. Most of the flux that you see actually comes from the atmosphere, and definitely all these bright things are skylines, OH lines in our atmosphere, and you may be able to also see some cosmic rays here and here, but the process will then be very similar. Finally, perhaps one of the most exciting developments over the last few years is to be able to do 3D spectroscopy. So you don't have to choose between doing imaging or spectroscopy. You can actually get an image and get a spectra for every single pixel. And perhaps the most revolutionary instrument has been MUSE on the VLT that you can see here. And essentially, MUSE produces a data cube that each slice contains an image at a specific wavelength. And then you can actually look through the data cube to look for emission lines, absorption lines, and be able to, for example, infer the rotation or understand the dynamics of the system that you're studying. This is it for section 7, where we discussed instrumentation, CCDs, how we actually get raw data and transform it to science data. And we've looked at some real examples of how real data looks like. As always, I would encourage you to read the lecture notes in detail and specifically to attempt the questions at the end of the section, that's section 7.4. If you're done with section 7 and all these contents, it means you've completed the first main part of 263, and you now have all the tools to start really doing astronomy. Sections 8 and those that follow will now target real astronomical objects and how we can use all the tools that we've covered so far to study them, infer their properties, and understand how they form and evolve. So I'll see you for section 8.